Did you know that the secret behind the perfect chocolate lies in differential scanning calorimetry, or DSC? Yes, DSC plays a crucial role in determining the melting point and crystallization process of chocolate. But what exactly is this DSC? Well, it's a thermoanalytical technique that measures the heat difference between a sample and a reference as they're heated or cooled. With DSC, scientists can observe changes in physical and chemical properties, and it's not just about chocolate. DSC has a myriad of fascinating applications in our everyday life, from determining the safety of pharmaceuticals to testing the durability of building materials. It's an essential tool in many fields, including food science, pharmaceuticals, polymers, and even forensics. So, if you want to unravel the science behind your favorite chocolate, stick around as we dive into the world of DSC. So, what exactly is differential scanning calorimetry? Let's dive right into it. Often referred to as DSC, it's a thermoanalytical technique that's all about heat. Specifically, it measures the amount of heat required to increase the temperature of a sample. Think of it as a thermal detective, meticulously noting the energy it takes to change a sample's temperature. Now, you might be wondering why heat is so important. Well, different materials react differently to temperature changes. Some might need a lot of heat to get warmer, while others might need only a little. This can tell us a lot about the material's properties, like its specific heat capacity and phase transitions. So, by measuring the heat flow in and out of a sample compared to a reference under controlled temperature conditions, DSC gives us insights into the sample's thermal behavior. In other words, DSC is a detective that helps us understand how different materials behave under diverse temperature conditions. Now that we know what DSC is, let's explore its different types. Differential Scanning Calorimetry, or DSC as it's more commonly known, is primarily divided into two main types: heat flux DSC and power compensated DSC. Each type is unique, serving its own special role in the world of thermodynamics. First, let's dive into heat flux DSC. This type of DSC is designed based on the principle of heat flux. It measures the amount of heat that is required to increase the temperature of a sample and its reference. Picture this: two pans, one with your sample and another as a reference, both heated on a single block. The heat flow is then monitored, and differences between the sample and reference are recorded. The beauty of heat flux DSC lies in its simplicity and the fact that it can accurately measure heat capacity. Next, we have power compensated DSC. This type operates on a slightly different principle. Instead of measuring the heat flow, it controls it. Imagine two separate furnaces, one for the sample and another for the reference. The power supplied to each furnace is adjusted to maintain the same temperature in both. The difference in power is then recorded as a measure of the heat flow. Power-compensated DSC stands out for its speed and ability to provide rapid and precise measurements. So what separates these two main types of DSC? Well, it's all about the approach. Heat flux DSC measures the heat flow, while power-compensated DSC controls it. The choice between the two comes down to the specific requirements of the experiment. Heat flux DSC is typically used when heat capacity measurements are needed, while power-compensated DSC is often chosen for its speed and precision. In conclusion, DSC is a versatile tool, with two main types, each with its own specialties. Heat flux DSC and power-compensated DSC, though different in their operation, both play crucial roles in the field of thermodynamics. So, whether it's heat flux DSC or power-compensated DSC, each type has unique characteristics that make it suited for specific applications. Now let's delve into the heart of DSC. Its instrumentation. At the core of a DSC instrument are a few key components that work harmoniously to facilitate the process. The first of these is the sample and reference pans. These are tiny containers often crafted from aluminum, in which the material of interest and a reference material are placed. The choice of reference material is crucial, as it has to remain thermally stable throughout the experiment. Next, we have the furnace. This is where the magic happens. The furnace heats both the sample and reference pans at a controlled rate. This controlled heating is crucial to ensure accurate measurements and to prevent any thermal shock to the sample. Now, let's talk about the detector. This is the component that measures the difference in heat flow between the sample and reference pans. It's this difference in heat flow that gives us the valuable data we seek. In essence, the detector is the eyes of the DSC instrument, closely monitoring every thermal event that occurs in the sample. And finally, there's the cooling system. While the furnace is responsible for heating the sample, the cooling system ensures that the temperature can be lowered when needed. This is particularly important for experiments that involve cooling the sample below room temperature, or when the sample needs to be cooled rapidly after a heating cycle. Each of these components plays a vital role in the function of a DSC instrument. The sample and reference pans hold the materials for testing. The furnace provides the controlled heating, the detector measures the heat flow, and the cooling system regulates the temperature. These parts work together like a well-oiled machine, each contributing to the overall process. It's important to remember that the quality of a DSC analysis is heavily dependent on the precision of these components and how well they function together. A slight deviation in any of these parts can lead to inaccurate results. So that's how the different parts of a DSC instrument come together to make this amazing technique possible. But how does DSC work? Let's find out. Differential Scanning Calorimetry, or DSC, operates on a rather fascinating principle. Now, imagine you're trying to understand a new song. You compare it to something you're already familiar with, right? Similarly, DSC compares the heat flow into or out of a sample with that of an inert reference. Picture this. Two pans, one holding our mysterious sample and the other an inert reference, usually a material that doesn't change its properties over the range of temperatures being used. Both pans are heated at the same rate. But here's the catch. The material in our sample pan may undergo a physical or chemical change, and when that happens, it will either absorb or release heat. Now, DSC is like the maestro of an orchestra, controlling and observing this performance. It carefully measures the difference in heat flow between the sample and the reference. If our sample absorbs heat, the DSC adds more heat to it to maintain the same temperature between the sample and the reference. If it releases heat, the DSC reduces the heat input. So let's say our sample is a piece of chocolate melting in one pan and our inert reference is an empty pan. As we start heating both pans, the chocolate begins to melt, absorbing heat in the process. So DSC, being the vigilant observer, detects this and adds more heat to the sample pan to keep the temperatures equal. This additional heat or heat flow is then recorded against temperature or time, creating what we call a DSC curve. This curve, my friends, is like a thermal fingerprint of the sample. It carries valuable information about the sample's thermal properties, such as its melting point, heat capacity, phase transitions, and much more. So by comparing our sample to a reference, DSC provides us with valuable insights about the sample's thermal properties. It's like deciphering the thermal language of materials, one sample at a time. Finally, let's look at some of the fascinating applications of differential scanning calorimetry, or DSC. While we've discussed the nuts and bolts of how DSC works, the real magic of this technology shines when we see it in action. Firstly, DSC is a go-to method for checking the purity of a substance. Since impure substances have altered melting and boiling points, DSC can detect these changes, giving us a clear insight into the substance's purity. It's like a secret agent, unveiling the true identity of substances. Next, we have the study of phase transitions. If you've ever wondered how substances change from one state to another, like from solid to liquid, DSC is your answer. It can monitor these transitions, helping scientists understand how and when these changes occur. Moreover, DSC is instrumental in determining the stability of a sample. It's all about heat, how much a sample absorbs or releases. By monitoring these heat flows, DSC can determine if a sample is stable or if it's likely to decompose, making it a vital tool in material testing. But it's not just limited to the lab. From ensuring the quality of your morning coffee to developing new pharmaceuticals, DSC is everywhere. It's used in the food industry to monitor the melting and crystallization of fats, and in pharmaceuticals to study drug stability. From the food industry to pharmaceuticals, DSC truly has a wide range of applications. So, that's a wrap on differential scanning calorimetry. We've journeyed through its definition, delved into its diverse types, and explored the intricate instrumentation. We've illuminated the governing principle and highlighted some compelling applications. Remember, DSC is a powerful tool in the realm of thermal analysis, enabling us to understand the physical and chemical properties of materials in a new light. Subscribe for more because you won't find me later. Dive into the fascinating world of science with us and discover the unseen.